who doesn't know who I am, I'm Peter Johnson. I'm an independent agronomist, and we're going to talk about nitrogen here, but we're really incredibly fortunate. So here with me today is Tim Laatsch from Koch. And Tim, give us a little bit of your background.
Yeah, sure. Thanks, Peter. I serve as the Director of Agronomy for Koch Agronomic Services for North America, and we obviously manufacture nitrogen stabilizers, so that's our primary business. I've been with the company about 4.5 years, and also live and work out of my home office where I have farmed for the last 25 years in Southern Illinois. So I've got a moonlight gig right in the corner.
So someday we will indoctrinate Tim into the fact that wheat is a real crop. We haven't quite got there yet.
Hey, I'm going to plant some wheat this fall, I can tell you that.
Oh, good man. Like after the last group is where you share this. Tim, thank you very much.
Best for last.
Anyway, so by the way, I think it's really cool because Director of Agronomy for North America, so he gets a really broad picture of many different factors around nitrogen, and nitrogen is really complex, right? By the way, how much is nitrogen in the news right now? Quite a bit, right? Quite a bit. So why are we back talking about nitrogen? Because it's in the news and because farmers have to do a better job. You can whine to me all you want about how the government doesn't understand, and I will agree with you, but it doesn't matter. We still need to do a better job, and we can't do a better job if we don't understand a little bit about that nitrogen. So just before we carry on, I do though, how deep's your topsoil? How deep's your topsoil? Just 3 inches? 6 inches? Yeah, 6 inches. How deep's your topsoil?
Well, I live in some of the poorer soil regions of Illinois, so it's about 12 to 15 inches.
Yeah. So, man, wouldn't you like to have that? Anyway, okay, let's go. How many people know what these are? What are these? Scott, what are these?
I can't remember.
Huh?
ISO something or other.
No, they're dosimeters, right? Or dositubes, if you will.
Yeah, I know what they're for.
What are they for, Scott? Measuring nitrogen gas. What kind of nitrogen gas?
Nitrogen oxide.
No! Scott! Kelsey, where are you? What kind of nitrogen? What kind of nitrogen? Because this is about loss. What comes off the soil if I put urea on it? What goes off as a gas? What form of nitrogen?
Nitrogen oxide.
We had a chicken farmer a couple of groups ago that uses these in his chicken houses. So what is he going to be monitoring for there?
Ammonia. Thank you very much, Jessica. Bingo. So we're measuring ammonia loss, right? So you take your household ammonia, you take the lid off, you hold it up to your nose. How do you like it? What's happening out of that, all that is a jug with water that the ammonia is dissolved in the water. That's all it is. What's happening in that jug? Why can't you hold it up to your nose? Because the ammonia in the water is gassing off, and that's what you smell, and that's exactly what we're measuring here, is the same thing. And so, these tubes, and I'll pass them around, but it's really kind of cool. They start out this pink color, and they turn yellow with the ammonia. So you can have a quick look. I'll just walk with both of them, and then we'll pass them around. You can see that they're pink and then they're yellow, right? And so in the chicken barn, when they turn yellow, that's all bad because that's telling you there's ammonia there. And so you can have a look. And this one is the control. And as you pass it around, you'll see that the tip of it is just a little bit yellow. So a wee little bit of ammonia gas came off that control, just enough to hit the 20 part per million level. And we cover them up with these blue boxes because we can't let the rain fall on them or we lose the data. Plus, we got to hold the gas around them just a little bit. They all have holes in them, so we're not keeping it all in, but that's why we're doing that. Cool. So, we're measuring the ammonia loss. You can see here we have about 20 part per million loss. And what Greg did, and by the way, you know, I give Greg a hard time lots, but for once, he actually did something right. It's really a rare thing, but this plot worked. We have a ton of stuff to show you here. And so what he did was he came in on last Friday, and he put these plots in place. And the first thing he did was take a garden weasel and work the strip. Why did he do that? Landon, why did you do that?
This is like having like a simple tillage method and a normal way to work.
Yeah, so it was a little bit of tillage, but why did you do it before you put the surface applied on?
So it's even all the way across the board.
Even, but also because the surface was fairly dry and we're trying to bring moisture up, right? We're trying to make it wet. So right out the gate, if it's dry, you don't get any ammonia volatilization. You get nothing because you need water to change the urea into ammonia. So actually I think it was Landon that probably did it. I don't know, Greg rarely ever does any real work, so.
No, I'll give him credit. He did that part because he wanted it done his way. You know?
Oh yeah, yeah.
So I did the rest for the most part. But
It's like, Lord help us, never let Greg drive. Like, it's got to be his way, but his way is generally not good when it comes to driving. Anyway, so he worked it up, and it wasn't quite wet enough, so I actually wetted it up, and then came in and put either a strip of urea or a strip of 28% right down in the band, and then put the decimeter tube down and put it on top, and we measured it. And so we can't tell you exactly what the numbers mean in terms of pounds of nitrogen lost per acre, but what we can tell you is that they're relative. So the zero nitrogen is 20 parts per million. The urea surface applied blew it right out, so we're over 800 parts per million. We don't know how much over 800. So what we can tell you is that this lost 40 times as much nitrogen as that did, because 20 times 40 is 800, right? So this lost at least 40 times and even more nitrogen than the control did. So why would we lose any in the control? Tim, why would we lose any in the control?
Well, we often see nitrogen mineralization during this time of the year, right? So organic matter in the soil, previous year's crop is going to mineralize. We're going to get a little bit of ammonium in released into the soil, and we could potentially lose some of that ammonium in. So we're getting just a little bit of background signal because of mineralization.
Yeah, absolutely. And by the way, there's another control at the far end that we won't get to. It's at zero. So that also tells you there's a little bit of chatter in the data. So as you look at these numbers, they're relative, but be careful that you don't say they're absolute, because there is a little bit of chatter in the data. So we put 105, by the way, 105 pounds per acre was the equivalent nitrogen rate. So a pretty typical application. Blew it out to water with the urea
Granular
surface.
application.
Sorry?
Granular.
Yeah.
Not
So this is
injected.
urea granule.
Yeah.
What? Urea granule. So we blew it out of the water with it on the surface. So tell me, what can we do to reduce that volatilization loss? Scott, what can we do?
Make it rain.
Oh, excellent, David.
yes, yeah.
So let's go to the rainfall first.
Yeah, so rainfall is actually the very best way to incorporate either urea or UAN. But the name of the game is having adequate water. So you've got to have enough rainfall to actually solubilize the urea, drive it down in the soil profile so that when the urea breaks down, your cation exchange can hold on to that ammonium nitrogen and not let it escape to the atmosphere. So how much water do you think would be adequate to get that job done? Any guesses?
3/10?
3/10 is close, but we need just a little bit more than that. So we need about ½ an inch of rainfall to get the level of loss down to about the same level that you would see with a urease inhibitor or nitrogen stabilizer on urea. If we drive that rainfall level up to about 7 to 8/10, we're gonna push that loss to near zero. So you need a healthy amount of rain. The worst case scenario that you can come against is when you don't have enough rain, but you have a little bit. So a little bit of water drives the process forward, but it's not enough to drive the urea down in the soil so that we can hold on to it.
So turn around and have a look at the corn crop behind you and the base of the corn plants. What do you see? I hope it's still there. It certainly is still here. I can still see it here. Moisture right at the base. So there was a 1 millimeter rain here last night. If you had Y-dropped nitrogen there, is that a good thing or a bad thing?
Not good.
It's all bad. because even though it took that 1 millimeter and funneled it, it did not get enough moisture. And this whole concept of dew, oh, the corn plant funnels the dew down to the base of the plant and it puts the nitrogen in the ground and that's all working good. It's all bull crap. It's 100% bull crap. So, I mean, if you got 2/10 of an inch, or maybe even 1/10 of an inch, that funnel effect could save you and get enough there to actually put it in the ground. But 1 millimeter, not enough. Dew, not enough. And actually, it makes it worse because that moisture makes the process go faster. So, Tim, I don't think we've mentioned to this group yet. So this is a worst case scenario, right?
Correct.
So we're warm soils, wet soils.
Yep.
How much do we lose and how quickly do we lose it?
Well, we can't measure it with the dosing tube method. It's really what Peter talked about earlier, being kind of measuring relative losses between the treatments. But what we know from existing field research is that under these kind of worst case scenarios, we can lose about 30 to 40% of our applied nitrogen to ammonia loss in a scenario like this demo that we set up here. So you think about, we put on 105 pounds, that means we're losing 35, 40 pounds potentially out of this application. And with nitrogen prices the way they are today, that's a pretty significant economic hit. And so, you know, we've got to try to find ways to prevent that loss from happening, right? Just spreading urea on the surface is not going to get the job done.
Right, but like Brian said in an earlier group, I have a couple days, right, before I got to incorporate it. Like, I'm not going to lose any in the first couple of days, or how long does it take?
Well, so Greg set this up last Friday, and he came out yesterday and wrote down the measurements off of the dosing tubes. So that's 6 days. All of this volatilization loss happened in 6 days. And probably the majority of it, if he had come after about day 3 and day 4, we would have seen most of the loss had already happened by that point in time. So under warm temperatures with adequate moisture, that process goes very fast. We blow it off very quickly. That biggest window of risk is really in that first 3-day window.
Yeah. And so think about manure, the same thing with manure. That first day is really quite critical. So, Scott, you said tillage should stop it, right? But you looked here, you're jumping ahead of us, and it didn't stop it. So why didn't it stop it? So
Not the right kind of tillage.
So, bingo, what's the depth of tillage? It's a garden weasel. How deep does a garden weasel go?
I'm not old enough. I don't know what a garden is.
It's one of those little, all the little wheels turn and they got little spikes on them.
It approximates vertical tillage.
Yeah. Anyway, if you come here and you look, it's about an inch deep and it's really loose and fluffy. So believe it or not, tillage can make it worse. But it is depth of tillage and whether you seal it after the fact. So if you put urea on a dry soil surface, no loss, because it's dry, you need water. If you take that urea, and with the garden weasel, we just incorporate it a little bit. So it's an inch deep that we work. Scott, if I work at an inch deep, where's the bulk of my nitrogen fertilizer? Half an inch, exactly, half the working depth. So now most of the fertilizer's in the top inch, and it's moist. And it's not sealed off. So shallow tillage, if you don't seal it off, actually can make it worse because it puts it into a wet zone. Now, if it's all dry, or if you get it deep enough, or if you seal it off after, then all of those things will help prevent the loss. But tillage doesn't necessarily solve the problem. All right, so let's move down here now.
It's got to be before it doesn't, it's got to be down 2 inches before it's not going to get lost.
And that is a super question, absolutely. And
yeah, the 3 to 4 inches is probably the recommended depth to minimize ammonia loss. Most of our tillage equipment isn't really adequate to get that job done unless we're direct banding and placing, that urea below the surface, maybe the strip till unit or something like that.
Yeah. And yep.
So if you're doing that, how does it compare? You've done it both ways. You put all your fertilizer on, broadcast it, work it in the spring, plant it, and things get sealed up. Versus you do half of it. come back like this. If this doesn't work, I'd like to better off.
Yeah, and we'll talk more. So I should have mentioned, by the way, Tim and I are going to talk nitrogen again this afternoon. And so maybe we'll come back to that, Bill, because it's a really good question. But if you guys want lunch, we would like to get...
And we will talk about split ends.
Yeah, no, 100%, because you're bang on with that question. But we'll show you what there is to see here, and we'll answer that after. Yep, Kevin?
What do you mean by seal it off? Like
So-
tell it.
Yeah, and so if you can get a layer of dust on the top, like you roll it, or you're got a really good harrow on the back that kind of pulverizes it and kind of packs it enough that there's not gas transfer. I mean, the weed weasel's not doing that, right? But that's if you can seal it off, pack it, you will significantly reduce the loss. Okay, so that was urea. Yeah, sorry, John.
How's that compared to NH3 injection?
So NH3 injection is simply like putting ammonia in the soil, and if you don't seal it, what happens? You burn the corn plant like crazy, right? Like you've all seen where the...
If it's a cultivator, is not sealing not taking place?
Oh gosh, we'll talk more about that in a minute, okay? But the answer, John, is no. And it depends, but the answer is really no. So here we have 28%. That was dry urea. This is liquid 28, UAN. What level of loss would you expect? They're both at 105 pounds per acre. We blew the top out on the urea. What would you expect on the UAN? Why should it be half, Scott? Bingo. So UAN, and by the way, you are the first guy today to actually have that answer.
We need a door prize.
Yeah, exactly. Like you get a free bottle of water, Scott. So UAN is urea ammonium nitrate. 50% urea, 25% ammonium, 25% nitrate. And the ammonium nitrate portion is effectively not going to volatilize. It can a little bit in really extreme circumstances, but we're not taking it that deep. It almost never happens. So 50% of your nitrogen is at risk. So 50% would be the right answer, give or take. And what's really interesting is this urea on the surface is 475. You double that, you're at 950. Cool. If we had taken the dosatube out at 800, right when it hit 800, stuck another dosatube in, it probably would have gone to 150 on the second, total 950, or who knows, but it is working the way you would expect it to work. And here again, surface incorporation, and it went to 600, and so that surface incorporation did not stop the volatilization. In fact, you would say it looks like it made it worse. Did it really or not? I mean, there is chatter in the data, but it is pretty interesting from that standpoint. Right?
Yeah, if you survey the literature, you're going to see exactly the same thing. We normally see about an average of 20% losses from UAN under worst case conditions like this across all different methods of application. And we'll get into some what would be deemed to be superior methods of application that don't get the job done either, depending upon how well you do them.
No, exactly. And by the way, just to show you the chatter in the data, that's UAN on the surface at 475. This is the exact same treatment because Greg stuck it in, or had Landon stick it in a number of times so that we would get, a little bit of consistency across, and it's at 600. So is this 600 actually more loss, or is it the same loss? It's certainly not less loss. So it did not reduce that amount of loss. So what else can we do to reduce those nitrogen losses? What are the other things?
Stabilizer.
Stabilizer, right on, Scott, stabilizer. So come on down with us.
You get paid extra that one, right? You get the free hat.
Yeah, you get the free hat, 100%. And so, so Tim, talk to us about stabilizers.
Yeah, so when we're talking stabilizers, that's a very broad and kind of general term. When we're trying to limit ammonia loss from urea or UAN, we have to pull the right tool out of the toolbox, and that tool is a urease inhibitor. There are many different urease inhibitor products on the market today. We've actually got here the UAN surface applied control against a couple of different products, Stabilizer A, Stabilizer B. And what you see is that both of these products were generally pretty effective at minimizing ammonia loss, reducing it to around, let's say, 15% of the untreated control. So anytime that we are surface applying or shallow incorporating either urea or UAN, we really need to consider mitigating risk of loss using a urease inhibitor.
And it is worst case scenario, but if you do that math, we lost basically 40 pounds where we didn't treat it. If you take 15% of 40, we lost 6 pounds. It's a really significant difference, right? And this just shows that they work, and but they should work because that's what they're supposed to do, right?
Absolutely.
Yep.
The chemistry is very well understood. We're inhibiting a specific enzyme that we know slows down the breakdown of urea, and that keeps losses to a minimum.
So anything else we can do to reduce loss? Scott's looking ahead, trying to figure it out.
I'm done answering.
He's got his prize.
He's got his prize already?
Peter, one of the things I do on my farm is I direct inject UAN.
Right on. So you're side dressing, and so that split nitrogen is another way to reduce loss. So come down to this last, and then we'll send you for lunch. And so where Tim is, we put on the 105 pounds of nitrogen, but what Greg had Landon do first is go in and create a 2-inch deep trench, right? And so what effectively we're doing is we're trying to get that nitrogen down in the soil. But when we put the 2-inch trench, did we stop any volatilization? 2-inch trench, put the product right in the bottom of the trench? Pretty obvious we didn't. Why not? Open trench. And so you win a prize too, Scott. I want you to win a prize. Not Kelsey. Yeah.
He wants the good stuff.
Crown Royal.
Oh no, if you want real rye, you don't drink Crown Royal. Oh my gosh. Anyway, let's carry on. So what's really interesting, and Tim coined this phrase, I like it, it's the slice and squirt. So many growers, when they side dress, we're running a straight coulter and a high pressure injection nozzle. Well, you know what? That slot is open. And when that slot is open, it's exactly like that. There's nothing to stop that urea turning to ammonia and gassing off. And in fact, it's a little bit like the worst case scenario, because now you've put it down in where the moisture is. And so you put it in a moist zone. You want to do that because you want it to be in the water to move to the corn plant roots. But it's in the moisture, it's converting to ammonia, and there's nothing stopping it from gassing off into the atmosphere. So if you are opening the trench or leaving the trench open, then stabilizers again work, right, Tim?
That's right. And so a great example, you'll see a picture this afternoon that I'll show you from my own farm this very growing season, where we came in with a coulter and an injection shank, but I strip till, and so that was applied between the rows. And that is effectively a no-till environment where we don't get good slot closure. And so in my case, knowing the system that I'm working in, I've got to manage the risk of volatilization loss from leaving that trench open. And so one way to do that is with a stabilizer, right? And we use that urease inhibitor. You see here, we reduce the loss from 475 down to around 100. So we're cutting it down to a fourth of what it would be otherwise.
Yeah, or
even, and again, both stabilizers pretty well perform to the same level.
Yeah. But when we close the trench, right? If we actually close the trench, then we're a winner, because now the soil is acting to prevent that gas from, it'll still convert, but it goes to ammonium. The ammonium ties up on the cation exchange capacity, and now Bob's your uncle. And so that's the thought process. Yep, Kevin?
Knives versus nozzles.
So knives versus nozzles, I don't care. The beauty of the knife is I know it goes deeper. The nozzles, like you think, but that slot is so narrow. like it's not going deeper than 2 inches most of the time. It just isn't. But and so, you know, take the stupid cast iron closing wheels off your John Deere drill and mount them on the back of your squirt and your slice and squirt. And as long as you close that, then you should reduce the majority of it. But I mean, I hate knives because they take too much power. But in general terms, you get a little bit better closure generally behind a knife because you've got loose dirt to work with. Anyway, either one can work. Anything else?
I love the sign right behind you there as well, because so when we stabilized with a closed trench, we actually drove the loss here to 0. But the question you got to answer, you know, is does that application pay for itself? You know, if I'm taking my losses from 60 parts per million down to 0, is that enough to justify using a stabilizer? And in this situation, it probably isn't. What it comes down to really is a measure of your confidence in how good a slot closure you can achieve. If there's any doubt, then you got to do something to mitigate that risk, and the stabilizer provides a nice option for that.
Cool. Yep.
You apply nitrogen the same time as you're doing planting with a slower release, and then it has a closure on the planter.
Yeah, and there's a whole lot of different planter options available right now. And so, you know, ranging from surface banding on either side of the row to putting it below below 2x2x2 or conventional 2x2 placement. Generally speaking, the deeper you go, the better off you are, right? If you're putting it on the surface, you still got the same issues that we've just talked about. And if you're putting it shallow, you may have the same issues. But when I'm going early season like that, my bigger concern, you know, we'll show you some data on this afternoon, is actually losses related to nitrification, which is a whole different loss mechanism that we'll talk about later.
Yeah, this is only one component, but on the planter is fine. The same thing still, the same principles still all apply. And there's other forms of nitrogen we haven't talked about, like ESN, the polycoated urea, which is another potential. But
Is that a longer time release? I guess.
so the polycoated urea is temperature and moisture, and it can be as bad as urea. It really can be, or it can be almost 0. So again, it depends on Mother Nature after that happens. It really does.
We've got a product, and you know, I don't want this to sound like a commercial, but it is an interesting product for that application. It's called Super U, and it's a urea that's manufactured with integrated dual inhibitors. So it's got NBPT, that's a urease inhibitor to make sure we don't lose stuff from up above the ground, but it's also got a DCD in it, a high concentration of DCD, so we can protect against the nitrification related losses. So it gives you protection against all 3 forms of loss. And when you're going early in the season, you need to consider all the potential avenues of loss that you might have.